So let's get going. Okay. Few administrative things to start with before we get into the meat of the discussion. Some of you who have looked at the course page in the last day or two may have noticed we no longer have Stephen as a TA. We are down to three. Stephen got reassigned. There was apparently some sort of imbalance in the TA distribution through the various courses, and Stephen got reallocated to 540. So those of you who are taking 540 will still have him as a TA in a different class, but he's no longer TAing 537. It is, we still do, despite that, still do have TA lab consulting hours at least sometime in the day, every day, Monday through Friday, with the remaining three TAs. So hopefully that's still, a convenient time you can make it. Let's see. The grading for Project 1 is underway. Unfortunately, I'm a little stuck waiting for something from the lab. They have not gotten back to me on some kind of infrastructure I need for that. Anyway, I will let you all know when the Project 1 grades are available. They will just be put in a little simple text file, basically like next to your README file in the hand-in directory, and you can just look in that file and see what your grade was. There will be notes on, if there were points deducted, what they were deducted for. I'll send out an email when that's available, just telling you exactly what the path of that file will be. Finally, there was ultimately at the end of class yesterday, one person who came up and said they would be willing to take notes. I told that person to email me, and I have not received an email from them, and I don't know the person's name or how to email them. So if that is you, please do email me. If anyone else decides they might want to take notes as well, that it is still an option, send me an email. There is a form you will need if you want to get paid for it. All right. So today we're going to be doing kind of a follow-on of the sorts of things we were doing in last week's discussion, which is sort of Unix concepts and things that relate to Project 2, which hopefully most of you have started by now. So you may recall last week we talked about forking and creating new processes. What happens if your child exits, but before your parent process has waited for it, you end up with this zombie state that your process ends up in, and you don't want to leave lots of those lying around. So you do need to use the wait system call to collect their exit statuses and kind of fully free the resources that the kernel is holding on to associated with that process that's no longer running, but still sort of leaves a little husk of itself lying around. The inverse is also something that may be of interest that some people have asked about with regard to the shell for Project 2, which is what happens if you have a process that forks and creates a new child process, and then the parent exits while the child is still running. You might expect that to also exit the child, or maybe leave a zombie-type parent, but what actually happens is that the parent exits cleanly, the child continues running, but in order to maintain the sort of tree structure of processes in the system in terms of what's a parent of what will happen is that the now orphaned child gets what is called reparented, or sort of adopted, by a special process called init. Init is always the first user process that a Unix system runs. It always has the PID of 1, and it's responsible for, once the kernel, when the system first boots, the kernel will come up, initialize the hardware and everything, and then essentially spawn this first initial process called init that is responsible for bringing up various system services, mounting file systems, doing various things like that. Once it's done that, and its responsibility then for the remainder of the time the system continues running is to adopt these orphan children. So if your shell creates a background process or something, and then the shell exits, that process then gets adopted by init, which is sort of the default parent process for anything whose parent has exited. And init then assumes responsibility for doing the wait syscall when that child process does eventually exit. So basically what this amounts to for your Project 2 shell is that if you do encounter that situation where you have like a background command running that someone ran with the ampersand syntax to skip the wait call in the shell, you can, and then you exit your shell, you can basically just leave it. You don't need to worry about cleaning up after a child that is still running. You do, however, need to worry about children that have exited. That's the concern with calling wait. You may have read, I think a few people have asked about, so I'll try to explain this a little more clearly, the deal with using wait or wait PID and the points in time at which you call it. Basically, what that is an attempt to simulate is promptly collecting children that have exited. If you have a bunch of children running in the child processes running in the background, you don't, if one of them exits in the middle of you reading a command or executing some other foreground command, you are not going to know that that has happened until you explicitly check for it. This is what you might call polling, in that instead of you receiving notification about something, you have to sort of explicitly ask about it every so often. So what I attempted to describe there in the project description here is that you do that at points in time in your interactive shell's execution that are about as frequent as you can reasonably do. From your shell's point of view, you will call fgetS or whatever to read a line of input, and that's, relatively speaking, a long period of time. It's a blocking operation. Your process, your shell, will get suspended in the blocked state until that line of input is ready, and then you become ready to run again. The kernel will schedule your process to read that input. But in that amount of time, that could be arbitrarily long. Similarly, when you're running a foreground task, you've forked and called exec on it to execute it, and then you wait. That's another thing that will block and can take a long period of time, potentially. So what I've described here is to encourage you to do those wait calls to check for any background processes that have exited immediately before you issue that prompt, and then immediately immediately after receiving that input. So it's essentially as kind of often as you can reasonably do in this model. In a fancier quote-unquote real shell, there are other more complex mechanisms you can use to actually receive that notification that a child process has executed asynchronously without having to explicitly ask for it. But that's a more subtle, fraught with problems mechanism that we're not going to make you deal with in this class. If anyone's curious, that's signals, specifically sigchild, in any case. Any questions on that? Okay. Let's see. So another thing people have been wondering about, or expressed some kind of uncertainty about, is file descriptors, which we touched on a bit in the last discussion, not in as much depth as I would have liked. Sort of ran out of time, and also I realized afterwards that I had misremembered how long the discussion actually is and mistakenly let you out 5 minutes early. So to go over file descriptors in a bit more depth, you may recall from the perspective of the user process that is using these file descriptors, they take the form of just a simple integer. It's 0, 1, 2. 0 is always standard in, 1 is standard out, 2 is standard error. Beyond that, they're whatever you end up with them assigned. The significance of that is that it's essentially just kind of an index into a table. Actually, I'm going to draw a bit here to hopefully make this clearer. To people watching on video, apologies, we're using the chalkboard here. So what you'll have is that you have some user process running, and it has, standard in equals 0, standard out equals 1, blah, 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 some other file equals 7. These integers are essentially indexes into a table. So if this is your proc struct, as you've seen in x86, that you'll probably need to modify for, xv6, that you'll probably need to modify for the xv6 portion of this assignment. So this is, the general data structure that the kernel uses to represent a running process on the system. There will be a component of that, that's your file table, your file descriptor table. And that's essentially just an array of pointers to another thing that's a struct that represents an open file. So while yes, a process can make up an integer, what's significant about the integer that is a file descriptor is that it is a reference, an index into this table of some open file that the kernel has set up for this process as a result of some previous system call. So when your process calls open, you pass open some path of a file you want to open. Open will return a file descriptor after the kernel picks one of these entries in this file descriptor table, creates a new open file struct for whatever file you have, and installs a pointer to it there, and then says, okay, that's going to be in slot number 4, and then 4 is your file descriptor for that open file. When you fork, as some of you may have discovered if you've started implementing your shell, you inherit the file descriptors of your parent process. Your child process ends up with a copy of this. So, harkening back to something we mentioned earlier with a similar sort of sharing in virtual memory, when we had, code pages being shared between different processes running the same program, can you guess what that might imply about this structure here, the open file? Some attribute it has to have? Something we touched on briefly? It's got a reference count, among other things, of course. But it needs that because you can have your process with some set of open files with references to these open file structs in its file descriptor table, and then it forks, creates a new one that has another copy of that same table with pointers to those same structs. If one of these processes then exits, you need to not close these files and free these structs in that exit system call, because there's still another process making use of them. So you need to keep track in each of these open file description structures of how many places those are referenced, hence a reference count. So these file descriptors are also, critically for this project, inherited, well, not so much inherited because you're maintaining the same process across exec-v or exec-ve, exec-vp. That's sort of the next thing we want to touch on, which is how you have a process run a program. So for those of you who aren't familiar, probably many of you have done this by now, but the function I sort of suggested you use for this is exec-vp, which is not actually the underlying system call. If what the system call itself is exec-ve, it's a little more difficult to use, not horribly so. It has a similar sort of signature. You pass it the path of the file, the executable that you want to execute. You pass it an array of arguments. You also have to pass it this array of environment variables, which is not super pertinent to this assignment, at least as far as I'm concerned. So there are, wrappers that I've encouraged you to use that don't, kind of automatically pass in the environment of the process you already have. The other key difference is in what this first argument means. In the exec-ve system call, the kind of raw underlying actual kernel syscall we're looking at here, that path has to be the actual path to a file that exists, that is the executable. Whereas what exec-vp does for you, which makes things a little easier, is to find that file given just its name. Normally, in a kind of full-fledged shell, it doesn't use exec-vp. It'll use the exec-ve underlying system call, and it has to do a little bit of work to, when you run, say, the ls command, find where ls actually is. You can see, if you want, what that amounts to with the command which just takes a command name and basically does that lookup. So what the shell has to do every time you run ls is search for the ls command. It finds that in the /bin directory, which is where a lot of commands are. most often they'll be in /bin or /usr/bin. And then it'll pass that path, bin ls, into the execve system call. How it does that search is looking at a special environment variable called path, which is a colon-separated list of directories in which it looks for commands. So first it'll check opt local bin, and there's no ls in there, and then opt local sbin, there's no ls in there. It'll keep going through all these colon-separated paths until it finally reaches /bin, where it finds an existing executable file called /bin/ls, and then it'll pass that to execve. What execvp does is basically do all that searching for you. So it'll check your path environment variable, it'll parse out these colon-separated directories that make it up, and then it'll check all of them and call the execve system call for you with whichever one of those exists. So that, simplifies your life a bit. Doesn't, it's not in my opinion, a super critical, interesting part of what a shell has to do. So I'm encouraging you to bypass that. If you want to implement it with execve, you're welcome to do so. But I imagine that's probably more tedious work than most of you feel like doing. So once you call this exec system call, in whichever form you do that, be it execvp or execve, you still maintain those same file descriptors that you had from before the exec system call. The exec system call will just kind of replace your running process. It has the same PID, it's still the same process from the kernel's point of view, but you're suddenly executing a different program. So execve does not return. It will return only if it fails. If you use execve and it's successful, it never returns. So the next line of code after you call it will never get executed. So let's look at a little demonstration of that. Right, where'd it go? Here. So this is just the same little demo program we were looking at last time, where we called fork and have a parent and child process. So let's try using this. So we'll call execve, or let's use execvp because it'll simplify things for us a bit. Let's run ls, and so we'll look at our main page here, as I encourage you to do. Many of your questions can be answered by careful reading of man pages. Not to discourage questions, but do read man pages first. Sometimes they can be kind of hard to understand. I realize the terminology they use might not be familiar to a lot of you, which is fine. But anyway, we look here, we see we have an array of pointers to strings. We look at how that has to be structured. It describes argv, which, okay, it's going to defer to execve here. So a pointer to a null-terminated array of character pointers to null-terminated character strings, which might sound kind of confusing. It is confusingly using null in two different ways, which some of you have had some uncertainty about, which is entirely understandable. Null can refer to both a null pointer, which is a pointer-sized thing with the value 0, typically. It can also refer to a null character, which is how C strings are terminated. So what this means is that you'll have an array of pointers, each of which is pointing to a C string that has a null terminator. So this will be foo and bar. So these are null terminated by these null bytes. These are your C strings here. But it's also saying that this array itself has to be null terminated, and that's going to be done with a null pointer, which is a different thing. In C notation, this will be written as single quotes \0, whereas this will be written with that all caps null constant macro that the standard library headers provide you. So you need to set up something like this in your C program to pass in the arguments to the program that you're executing. Recall from having written C programs that use argc and argv, the first element of argv is just the name of your program. So we'll just construct a little simple one here. Sorry. Let's go character, pointer, array, argv, and then we'll say ls, because that's the program we're going to be running, and then let's run it on slash, the root directory, and then we'll terminate it with a null. So we'll pass that in, and except, what about our next line? This is no longer appropriate to have here, because as we said a moment ago, execvp, if it works right, is not going to return. So if it does return and we in fact get to this next line, 0 is the wrong thing to be exiting with, because we want to indicate that something went wrong, so we should change that to a 1. So we'll attempt to call ls on slash, the root directory of my file system, to just list whatever's in there, and then we'll exit. Well, really, if everything goes according to plan, ls will, take over this child process. We will never reach this exit line, and ls's exit status will be the exit status of our child process. But if we do fail for some reason, we'll exit non-zero. So let's compile that. Seems to have worked. And then, right, we still have this doing get char here, so it's waiting for input. But we can see that we did, in fact, run ls on some directory. If we want to add in another argument, let's say a -l, so that ls, prints in the long form listing. We can do that too. So now we see everything that's in the root directory of my file system. So that's the basics of how you use the execvp system call. You'll need to do that in your shell to execute any command that's not one of the 3 built-ins. So cd, pwd, and exit, should not be implemented with execvp. As mentioned in the project, cd and exit fundamentally cannot be. pwd you could, in theory, execute. I think there is actually a pwd command, but for this project, you should, as most real shells do, implement it as a built-in in your shell. The way you do that, some of you have asked about, is get cwd. As mentioned in the assignment, this just returns what the path name of your current working directory is. You should not have to, there is actually an upper limit. Some of you have wondered about how large you need to make this buffer. There is, in theory, an upper limit on that, but I'm hesitant to encourage you to use it, because if you do this kind of appropriately, you can, avoid having to know that. So I will encourage you to read this description and think about how you can use getcwd to not have to care about how big the buffer is that you pass to it. Let's see. Any questions on file descriptors, inheritance, execvp, dupe? I guess we haven't talked about dupe. So dupe is a way that the shell, or dupe2, and as recommended, is how the shell can set up more explicitly what file descriptors are going to be what. And you'll need to use that to implement the greater than and less than, standard out and standard in redirection operators that are part of the assignment. So dupe basically takes an existing file descriptor, or dupe2, and creates another file descriptor for that same open file. So what that'll do in terms of this diagram is basically just, if you have entry number 0 here referring to that, and you call dupe on it, it'll give you a new file descriptor, install a second pointer to that same open file, bump its ref count by 1, because now you have 2 file descriptors referring to it, and return you whatever number, or the number of the slot that it put that new duplicate file descriptor in. This might sound kind of useless because you already have a file descriptor referring to this file. You might, just use that one. Why do you need this redundant copy? The reason it's useful is so that you can control exactly which file descriptors refer to what. So recall that standard in is always 0, standard out is always 1, standard error is always 2. If you want to arrange those file descriptors for your child process, or sorry, for the new program that you're executing via execvp or whatever, you need to arrange those so that they refer to, for example, whatever file name was given to your, after your greater than symbol or after your less than symbol for standard in. So there are a couple ways you can do this. I would recommend, as I did in the assignment, using dupe2. It's a little more direct. that just lets you explicitly specify what file descriptor you want the new one to be. And if there is an existing file descriptor that has that number, it'll get implicitly closed. Dupe2 is a somewhat more recent addition. Originally, in the olden days of Unix, you only had dupe, and you relied on what is considered by many people, myself included, to be kind of a mistake in the Unix system call design, which is that anytime you create a new file descriptor, whether it's by open or by dupe or whatever else, there are various other ways you can end up with file descriptors, it always allocates you the first unused number in your table there. So it'll go for any open slot and take that first one. So what you do, if you wanted to control which slot your new file descriptor ended up in, say you want to set up standard in, you'd close whatever your 0 file descriptor, your existing standard in is, thus freeing up that slot in your file descriptor table. Then when you call dupe, it's going to be guaranteed to give you 0 as the next file descriptor for your now duplicated file. You can then close the original one, whichever file descriptor you passed to dupe, because you're not going to be using that one anymore, because the only reason you opened that one in the first place is to set it up as standard in or standard out for your new command. Now that you've done your dupe to install that file descriptor in the right place, you can get rid of it. Questions on that? Have people implemented this already? Is this one? Yes, a few people. Yeah? Well, so once you call, it depends on which process you're referring to. So in the parent, you shouldn't really need, well, it depends. There are multiple ways you can do it. The kind of neater, more elegant way would involve the kind of long-lived parent shell process not really ending up with any new file descriptors, because you can fork, and in your child process that is going to become the new command that you're executing, do the open and whatever file descriptor manipulation you need to do only in the child. And then when you call exec, that child, that process continues to exist, but it's no longer your shell. It's a new program that is whatever, ls or whichever command was specified in the command that was entered. And that process will do whatever it does. It's not your concern. It's just, it's not the shell's responsibility to enforce rules about how its child process handles its file descriptors. It's just there to execute it, and that program can do what it wants. You will need to, if execvp does fail, for example, if you type in a bogus command that doesn't exist, and execvp does return because it didn't find a command named whatever you typed in anywhere, in that case, yes, you'll need to close those file descriptors, because you don't want to have, file descriptors are another thing you can leak. Like processes and memory, things you create that you allocate, you need to ensure get cleaned up properly when they're no longer in use. So if you do have that situation where someone runs a non-existent command with standard out or standard in redirected to some file, you open a file descriptor to refer to that file, do your dupe to set it up appropriately, you call execvp, and execvp returns an error because the command didn't exist. You then need to close that file descriptor. Otherwise, you'll gradually fill up your file descriptor table. There is a maximum size that it'll enforce, and eventually you'll run out of file descriptors and be stuck. So yes, there are situations where you do need to be concerned about closing file descriptors. Actually, Valgrind will tell you about that. If you leak a file descriptor, I believe, or there's an option in Valgrind. Oops, wrong machine, sorry. I believe it's track FDs, yes. If you add this flag to your Valgrind command line, I encourage you to use Valgrind on your shell. Use it early, use it often. It will detect lots of errors that might otherwise go unnoticed. You can add this additional flag to your Valgrind command line to tell it to track file descriptors. And then if you do have a situation where you leak a file descriptor, it will warn you and say, hey, you opened file descriptor number 4 and never closed it before you exited. That's something you should clean up. Other questions on what we've talked about so far? Okay. Sorry, was there another there? No? Okay. Let's see, to touch on a few other things that people have asked about. There's been some confusion about the interactive versus non-interactive mode. That's basically just aiming to get you get your shell capable of supporting script style execution. So if I, create some file that I'm going to call script.sh and put a command in it like ls, I now have that command sitting there. I can run bash on it, bash being my shell that I'm using here, for this demo. Most of you are probably also using bash too. Sorry, sorry, that was the content of the file, not its name. Ignore that, please. There. If I run bash on my script file that I just created, it will, instead of reading commands from my terminal that I'm typing into, it'll instead read commands from that file and execute them as a script. So here you see the output of ls, same as if I'd run it from my prompt here. Similarly, if you put commands into a pipeline, remember the pipe demo we had last time, bash's standard input will then no longer be my terminal, it'll be this pipe, which is connected to the output of the command before it on the left of the pipe. So echo, if you're not familiar with the echo command, that just prints its argument. If I do echo ls and pipe that into bash, again, it's going to read that and execute commands from its non-terminal standard input as sort of a script. Usually you don't refer to it as a script if it's not in a file, but it's automated, non-interactive input. So finally, if you just run bash, this is going to be a bit confusing because I'm already running bash. I can run a second instance of bash from here that, never mind, forget that, but I'm now in a kind of sub bash process beneath my initial one. And if I exit out of that one, I'll find myself back at the initial one. So those are the kind of three modes of operation you need to support. Mostly, it shouldn't be too difficult to do that. You basically just need to check the two conditions described at the beginning of the project. Basically, whether or not there are any command line arguments. If there is one, you're running in script mode, so just read commands from that file. And if you have this isAtty function, if that returns zero on standard in, recall the standard in file descriptor is 0. If you call isAtty 0 and it returns false, essentially, that means that your standard input is not connected to a terminal. So you're not having a user typing in commands, so don't print a prompt, is basically the only difference. So you have these two modes. Either way, you're just going to be reading commands from a file descriptor or optionally a C library, all caps file. You can use either one for that. Should be okay. But the only real difference is, aside from having to do this detection, once you've determined which mode you're in, it's basically just whether or not you print a prompt before reading your command. Let's see, what else was I going to cover here? Another thing people have asked about is if you have background processes running when the shell exits. We can demonstrate this. A good rule of thumb, if you're still uncertain, go ahead and ask, but a good rule of thumb to start with is, what does bash do? If you have some question about how your shell should behave. If you think it might be if you're not sure how it works, or you think it might be difficult to implement, of course ask. There are lots of fancy things bash does that you do not need to implement. But for example, in this case, we can, so I will start a sub bash here. So I'm now one level down. I still have my parent original shell sitting there, but it's waiting for this new bash process that I've started to exit. So if I just run the sleep command, that's going to sleep for however many seconds I tell it to. So if I sleep for, say, 100 seconds in the background, I now have that process. I can use the ps command on 49698 and see sleep is still running there. If I then exit my inner shell, so now I've exited my parent process, my sleep, let's see, is still running. So this fits in with our general rule of thumb, basically answering that question as, if you do have background processes still running at the time you exit, let them be. Init will take them over, they'll get reparented. You don't have to worry about them. You don't have to wait for them to exit. You don't have to kill them or anything, just let them go. So, less effort. That should be good news. Any other questions relating to that? Okay. Let's see. Another little debugging tip that might be useful with Valgrind for this, oops, and again I'm on the wrong machine here, is with Valgrind you now have, at least from Valgrind's perspective, this strange situation where Valgrind is running your program, tracking all its memory access and everything, but then it calls fork or it calls exec, and now you have a different program running or you have another process. So that's where this flag might come in handy. There might be situations where you actually might not want to use this, but if you are encountering errors in your child process, after you call fork, in the branch where fork returns 0, indicating that you're executing the new child process, you can have Valgrind follow along with that child if you pass it this trace children flag, so that when you do, sorry, oh no, I take it back, I misread this. This is for following beyond exec, which you actually almost certainly do not want, because unless you are using your shell to execute another instance of your shell, which should work, but I don't see why you would probably be interested in trying unless you're exercising Valgrind, you won't want Valgrind to continue tracking errors in, if you execute ls, debugging ls is not part of this problem, part of this project. Plus, you're probably not likely to find any errors in ls. So, anyway, basically never mind on that. Sorry, I was confused about. Sorry? Right, it does, but that's because it kind of has to. So what actually, perhaps, well, yeah, because of the way Valgrind works, it doesn't actually execute your program directly. It's sort of a simulator, or it's almost actually kind of an interpreter for the x86 or whatever machine code in your program. So given how fork works, recall that fork works by creating a new copy of the entire virtual address space of the program that called it. So what that's going to do is create another instance of Valgrind, and Valgrind is interpreting, reading machine instructions and executing them in this sort of simulated CPU that it uses entirely in software. Your program's instructions are not executing on the CPU; they're being read and simulated by Valgrind so that it can check everything carefully. The new process that you create with fork is going to be another instance of that. It's not going to suddenly start magically executing directly with your process's instructions on the CPU hardware. It's still going to be another instance of Valgrind interpreting your instructions. That I realize that might potentially be kind of confusing. Don't worry about it too much. Basically, this is just explaining that Valgrind doesn't really, well, as it says here, would be difficult not to. There's not really a good clean way for Valgrind to not continue tracking, checking your memory accesses or whatever it's doing in the child process after you call fork. But you can optionally have it follow exec as well. That's what this option is doing. However, what definitely you may want is in GDB. Sorry, man is probably the wrong thing to do there. GDB has built-in help. You can maybe some of you have discovered this at the GDB prompt. You can type help on the set command. In that email I sent out last week, there was a set command for setting your prompt. That's what I've got here to get mine in green, which I find a little easier to read. There is a set command that we probably just scrolled by here. Where did it go? Yes, here. So this is an option that you actually probably want to know about. So if you are debugging your shell under GDB, and, well, by default, follow fork mode is parent. So that means when you're running your process under GDB and that process calls fork, GDB will remain attached to the parent. The child will be, loose, so to speak, not directly under GDB's control. If you want to do that the other way, you can set follow fork mode to child, and then after you've made that setting, that's not going to magically transition you to the child once you've passed the point where fork was called. But if you do this set follow fork mode child before you call fork, then once you do, GDB will instead follow the child and leave the parent detached. So you can investigate whatever problems you might be having in your child process between where you call fork and maybe where you call exec. Because at that point, again, once you call exec, it's no longer your shell, it's suddenly a different program, and you have nothing else to debug because it's no longer your code. Questions about that? Are people generally comfortable with using GDB? You've been using it heavily? Not at all? Some? Hopefully at least some. Okay. Let's see, one final thing that, well, I don't know if any of you are curious about this, but it might be sort of interesting. There was a brief mention at the end of the XV6 portion of these commands true and false. Anyone know where these or originate or know what they're used for? You can see where they live. They are actual commands. You know, if I execute bin true, it's going to return 0. The kind of real shell way of looking at an exit status is with this $? So we can see it exited 0. And bin false always just exits 1. I also happen to have my prompt set up to colorize this in red when something exits non-zero. So that's a little indicator. But what those are useful for is mostly, at least I find, in shell scripts. So like we demonstrated just a moment ago with this file, you can put shell commands in a file. Let's just make that one go a little further. So here's my shell script. Shells also will support, you know, it is quite arguably, in fact, I think it's sort of underappreciated as such, a programming language. You know, you can have conditionals. You can say if some command, then some other command, and this is a little weird for strange historical reasons. You terminate an if with the phi keyword, if backwards. Don't worry about that. But what this, so this actually relates to, pardon me, these machines' keyboard shortcuts are very unfamiliar to me. This relates to another portion of this assignment. Anyone want to guess what attribute of this some command is used as the conditional for determining whether we go into this if block or skip it? Something we've talked about a few times, and it's the central focus of the XV6 portion. Exit statuses, right. So what this syntax means to the shell is execute this command. If that command returns 0, it's regarded as successful. So it's actually sort of backwards from how you're probably used to thinking about, you know, Booleans in programming language. 0 is success or true. Non-zero is false. So if I run some, you know, true here, this is essentially how these, or at least I'm not sure how widely they're actually used this way, but for me, it seems like the kind of obvious, convenient way to use these commands. That if you execute something like true here that exits 0, indicates a success with its exit status, then you'll go through and run this. So we'll just demo this here. And of course, you can have an else block as well, except I typoed it. So we'll just take that out for a moment. So if we then run bash on my script here, it exits. It prints success because I told it to do that if true, you know, exit 0, which of course it's going to do. If we instead put false there, the false command, as we saw earlier, is going to exit 1, and so we'll see failure. This gets convenient if you want to have that Boolean be a variable. You can, you know, these are things you do not have to implement in your shell, of course, but in a more kind of powerfully scriptable shell, you can have variables. So, you know, some var equals true, and then maybe if something else, that variable gets set false. And of course, I've got the then there. You can then refer to that via a variable. So this variable, which you use with the, pardon me, I'm doing it again. dollar syntax in front of a variable name to expand to the contents of that variable. Before it executes it, it'll see this dollar sign, go, okay, well, what's the value of this variable? And it'll substitute in either true if we did not execute this if block, or false if we did, and then take the expansion of that variable, execute that as a command, and you then essentially have a way to store booleans in a shell variable and use them for control flow and things like this. So if you're interested in shell scripting, it's, I don't know, maybe some of you looked at the little test script I handed out for the P1 sorting program. You know, it is actually a relatively full-featured language. You can define functions in it and so forth. You can, you know, do things like recursion. Well, it's very limited in other ways. Essentially, all your variables are strings. You can't, well, Bash has arrays, but you don't have pointers or anything like that. You don't have structs, but you can still, there's still a fair amount you can do with shell scripts, and it can be a fairly powerful way to tie together programs, sort of like that demo we looked at last week with, you know, building a word counting program out of a handful of commands. Questions? Yeah. Yes, I again, like the P1 sorting program, I'll send out a script, hopefully by the end of this week, with some basic, you know, it's not going to be fully testing everything you need to do, but it'll, you know, ensure that you're not doing something, you know, way off in the wrong direction. It'll probably just test, you know, basic script mode. It probably will not test interactive mode because that's kind of harder to test in an automated fashion, and I assume that's probably how most of you are testing your shells as you're working on them, so I assume that's probably well covered ground by your manual testing. But yeah, it'll, you know, make sure your command's getting run right and maybe do some simple testing of the like redirection operators or something. But yeah, I'll probably do that in the next few days. Other questions? Have people started the XV6 portion yet? Anyone? Yeah. In XV6? Oh, the third portion of the XV6 portion? Right. So yeah, at least a few of you emailed on the first XV6 project asking about this error message you saw sometimes when your like get fork count program would appear to run correctly, but then after it ran, you'd see a message saying like trap 14 or something with a bunch of hex, you know, numbers interspersed. What that is cryptically telling you in the original unmodified XV6 is that you know, just returned straight from your main function rather than calling the exit function. The XV6 C library is unfortunately not sophisticated enough. Okay, I see we're out of time here, but stick around if you want to hear. The XV6 C library is not sophisticated enough to support returning directly from main. So what happens there is that you don't have a function that called main. You just, when you call exec, you know, exec VE, it'll jump right to the start of the main function. And then if you return from that, there's nowhere to return to. So it jumps to an invalid address and traps, and you know, it's essentially, it's not really significant because your program is already about to exit, but you essentially crash right at the end of your program. So what this chunk of the assignment is to do is to modify the XV6 user space support. You need to make a little tweak to a make file and a little tweak to one of the user space C files to add a little function that sort of gets inserted there as the entry point when you call exec VE on a new program, so that you jump to that function, and that function bounces to main, and then main can return to that function, and that function takes care of calling exit, is basically all it is. Clear? Hopefully? Okay. Yep.